So today's lab is on Taylor polynomials. And so I feel like I first owe you some explanation of what is a Taylor polynomial, all right? So suppose we're given a function, all right? So here's basically the problem. Given a function f of x, how can we approximate f of x using a polynomial centered at x equals to a. So I think the first thing I need to tell you guys about is what do we mean by a polynomial centered at a? All right? So a polynomial centered at a is going to look like this. Something like p of x equal to, say, c0 plus c1 times x minus a plus c2 times x minus a squared plus plus cn times x minus a to the n. So this is this is not the usual polynomial, right? Our usual polynomial is what? It's not centered at a, it's centered what? We usually center polynomials at 0, right? So like, a equals to 0 gives polynomial in what? What we call standard form, right? So that would be a special case, right? Just c0 plus c1x plus c2x squared, and so forth and so on, right? So the insight of the Taylor polynomial construction is identifying what these constants c0, c1, c2, all the way out through cn, what they have to do with the derivatives of the function, all right? So let's just discover it. So suppose, f of x is equal to p of x for the moment, all right? Then let's find some derivatives, right? So, all right, so first of all, we have f of x equals to c0 plus c1 times x minus a and so forth, right? Then we have f prime of x. What is f prime of x equal to? So here, these are constants, right? So the derivative of c0 is 0, derivative of c1 is just c1 again. So this differentiates to c1 plus 2c2 times x minus a plus 3c3 times x minus a squared until we get to n cn x minus a to the n minus 1 by the power rule, right? Do you guys follow? All right. What happens when we take a second derivative? We get 2c2 plus 3 times 2 times c3 x minus a, right? And then so forth and so on. N times n minus 1, cn times x minus a to the n minus 2, right? What happens when we take a third derivative? Yeah, 3 times 2 times c3, the x minus a differentiates away. And then the next thing up the chain would be 4 times 3 times 2 c4 x minus a, if you kept track of it. And then the final one, n times n minus 1 times n minus 2 x minus a to the n minus 3, right? And if you see the pattern here, we just keep doing this, right? What's the nth derivative at x equal to? Well, it's, let's see here. So we led with a 3 with 3. We led with a 2 with 2, a 1 with, right? So the lead thing is n times n minus 1 times n minus 2, 3 times 2 times 1, Cn. And I've dropped my Cn. There was supposed to be a Cn there, right? There you go. So this is the derivative of a polynomial, the first, the second, the third, all the way out to the nth derivative of the polynomial. What happens if you take an n plus 1th derivative? Well, we get 0, right? Past this, the derivatives are 0. Okay? So what happens then is if we evaluate each one of these at a, what do we get? What is f of a is what? What's f prime of a equal to? What's f prime prime of a equal to? What's f prime 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 of a equal to? And so forth and so on down the line. What's the nth derivative of a evaluated at a equal to? So see what happens when we plug in a into here? We get 0 all the way on out. Everything except for the first term is 0. So we just have that f of a is C0. What's f prime of a? Again, everything past the first term is 0. So f prime of a is C1. What's f prime prime of a? Yeah, 2C2. What's f prime 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 of a? It's 3 times, 6 or 3 times 2. I'll write it as 6, sure, why not? 6C3, right? And so finally down here, n times n minus 1 times n minus 2, 3 times 2 times 1, Cn. So we can solve these equations for C0 through Cn, right? So what's C0? Well, C0 is C0 is f of 0, right? Or rather, f of a. C1 is f prime of a. C2 is 1/2 f prime prime of a. C3, 1/6 f prime 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 of a, and so forth and so on down the line. Cn is, well, see, at this point, it's nice to have a name for this pattern we're seeing, all right? So in mathematics, do you guys know what this is called? When we have n times n minus 1 all the way down to 3 times 2 times 1. Have you ever seen this before? Probably not. Like, it's not uncommon for it to not come up in mathematics before this, but this is n factorial. All right. So we could write this as 1 over n factorial times the nth derivative at a. Notice the parentheses for the nth derivative, right? So let's put it all back together. What did we just learn? We learned that f of x is equal to f of a plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared plus 1 over 3 factorial f prime 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 of a times x minus a cubed all the way out to 1 over n factorial, the nth derivative evaluated at a times x minus a to the n. All right. Now, this is actually a straight equality if we've assumed that f of x is a polynomial, right? Like that's literally an equality if f of x is a polynomial. But more generally speaking, if f of x is not polynomial, but, you know, the derivative, let's say the jth derivative at a exists for j equals to, 0, 1, 2, and so forth and so on, as much as you want, then the above expression, this right here, this is what's called the Nth Taylor Polynomial generated by x. Nth order Taylor polynomial for f of x centered at x equals to a. And in the lab write-up, in lab 3, I think I've used the letters were a little bit different. I think in my lab, I used I think I used n for like the summation, whereas I used k as the, I think I wrote this in the lab. It's not really different though. Tk of x is equal to the sum n equals 0 to k of f n at a over n factorial times x minus a to the power n. But that, of course, is equal to f of a plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared, all the way out to 1 over k factorial, the kth derivative at a times x minus a to the power k. So however you want to, I can see the difference. The distinction is here, I let n be the top power, whereas here I'm using n as the summation, like the index of summation. Sorry, it'd been better if I'd used the same notation both places, but anyway, this is what the Taylor polynomial is. Can you guys tell me, before I stop talking about I'm not going to talk much about the general theory, pretty much just this spiel here, and then I'm going to work through the first part of it with you. Like part 1 in the lab, I think, is not with a computer, it's just by hand. I want us to actually work it out on paper, to get started. Can you guys tell me what is if I said y equals to, f of a plus f prime of a times x minus a, what would that be? Very good, that's the tangent line. And so what is the tangent line? This is also T1 of x, right? So the tangent line is the first order Taylor polynomial, right? So the best linear approximation to the function is given by like this. The best quadratic approximation to the function is given by all these guys. And then if you want the best kth order approximation to the function, you take all the way out to here. So we're going to look at today how these formulas work to approximate functions, right, which may or may not be polynomials. Like if it's a polynomial, we're going to see something really nice happens. But if it's not a polynomial, generally speaking, to gain perfect accuracy of the polynomial representing the function, you have to just keep going and going and going. That's something we talk about in calculus too. That's what's called a Taylor series. Now, we're not talking about Taylor series today so much because we're not going to let these things go on and on. They're going to stop at finite order. That's why it's called the Taylor polynomial, right? So let's look at I'll help you guys with the first part of this.
So do you want the first part on paper or the first part on computer?
That's a good question. What? Oh, sorry. I need to. I forgot my computer needs to be logged. I gotta log out. Just bear with me here a second. I have. To remember my current password, you know. Just changing passwords every 6 months. It's no good. All right, let's see here. Come on. All right. So let's see here. Ah. Oh. So I knew something was. So the first number one, there's nothing to do, right? First number one is just a discussion. We've had that discussion now, right? But the second number one, there's something to do. That one, I want to do actually the the second number one and the number two. I want to work through with you guys. Let's start with number one.
Do you want that one on paper?
You can, if you wanted to, you can take it on paper and then take a picture of it with your phone and like cut and paste it into there. That'd be fine. Would that be good? Either do that or like type it out with the word editor. I think it's easier to write by hand and take a picture, personally. Or you could take a picture of my work on the board, whatever you want. I'll work with you guys on these two. See, number one was, what was it? It was x cubed plus 3x squared plus 7x plus 1. That's f of x, right? And we're supposed to do what?
Find two derivatives since we're at a.
Yeah, with a equals to 1, right? So that means we need to calculate the derivative, second derivative, third derivative, and evaluate those at 1, right? So like, what's f prime of x? What's f prime prime of x? What's f prime 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 of x? What are those equal to? So we got what? 3 plus what?
7.
Plus 7, yeah. And then second derivative?
6x.
All right. Third derivative? Just 6, right? Okay. So what's f of 1 equal to? What's f prime of 1 equal to? What's f prime prime of 1 equal to? And what's f prime 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 of 1 equal to? So 12? What's f prime of 1 equal to? 16, right? I got 12, yeah. We got 6, right? Now we can put together T3 of x, right? So T3 is f of 1 plus f prime of 1 times x minus 1 plus 1/2 f prime prime of 1 times x minus 1 squared plus 1 over 6. That's 6 is 3 factorial. By the way, I got distracted. I meant to tell you guys, this factorial, there's some special cases that I kind of have to like define. Just, you know, this is just a definition. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2, etc. All right, but the 0 factorial being 1 and the 1 factorial being 1, that always catches students off guard a little bit. It is just a definition. So 1/6 f prime prime of 1 times x minus 1 to the cube, right? There you go, that's T3. Now plug in the numbers that we have, 6, 16, 12, and 6. What do we got? Mm-hmm. And let's see here, what's 1/2? 1/2 of 12 is, yeah, 6. And what's 6 over 6 is 1, so. So I think that's kind of neat, right? There you go, that is the third order Taylor polynomial.
So you don't have to, so like the second one, the second row on the right, that would be the answer. You don't have to like go through and divide it out.
Oh no, you don't want to. If you multiply this back, yeah, if you multiply this back out, you know what you're going to get?
Okay.
You're going to get this again.
Okay.
So this is kind of an interesting algebra trick. This means we can take any polynomial in standard form and you can recenter it at another point by using this.
So when we type our answer here, how do you want us to type it like?
So for number, the second number 1, my apologies, you could like take a picture of this and cut and paste it into your lab, since you're here. You could write it out on a piece of paper yourself, take a picture of it, cut and paste it into there. You could alternatively use Microsoft, like the word editor, and type out, you know, T3 of x equals to this. So it's up to you. I think taking a picture of this is a good idea, because then you have a record of how we found it, you know. I'll work through number 2. Let's see here, number 2 is what? We're supposed to find the third Taylor polynomial for, what was it? F of x equals 1 over 1 minus x squared. And where were we centering this? 0, okay. Thank you. For, what was it, f of x equal to 1 over 1 minus x squared, right? Okay, so what's f prime of x? We've got a 2x over 1 minus x squared, right? And so technically there's a, fine, let me do it this way. Minus 1 over that times minus 2x, that's the chain rule. So we have a reciprocal function, like 1 over the something. So the derivative of the reciprocal is minus 1 over the denominator squared. And chain rule says multiply by the derivative of the denominator, which in this case is 1 minus x squared. That gives us a minus 2x. So clean that up, and we've got 2x over 1 minus x squared squared. What's f prime prime? So I have to differentiate that, right? So I get what? I get 2 times 1 minus x squared squared minus 2x times, well, 2 times 1 minus x squared times minus 2x by the chain rule, divided by 1 minus x squared squared oh, and this is, I'm still not done, am I? Because I have to square that denominator of the above, right? So this is starting to get to be a pain, right? The third derivative is going to, I mean, we can do it. Let's see here. Try to clean this up a little bit before I go on. So I have a 1 minus x squared times a 2 times 1 minus x squared minus, let's see here, 2 times 2 times 2 is 8, but I've got a minus and a minus, which is going to be plus 8. Is that right? So I think at this point, like, it would be wise to use some kind of computer algebra system to check us, right? So I think this would be a good point to open up Wolfram Alpha and see if we've actually calculated this correctly or not, made a mistake, what happened here. I get 10 minus 2x squared over 1 minus x squared to the 4th power. But I do, if this was my homework and I was turning it in for a grade, I would definitely have opened up Wolfram Alpha and checked myself, So let's see here, we got what? 1 divided by 1 minus x squared. So for the derivative, it gives me 2x over 1 minus x squared squared, which is what we got. For the second derivative, I got, oh, what? Huh. Looks like I lost something. Oopsie. See, I made a mistake. Where I made the mistake was right here. I had it 1 minus x squared squared, which I seem to have, no, I kept it there. But Wolfram Alpha has 8x squared. Well, I suspect Wolfram Alpha's answer might be the same as mine. It's just presented differently. But it has like, let me scroll down a bit. Sometimes Wolfram will give a couple different formats to the answer. Well, No, I think I made a mistake there somehow. I've got an arithmetic mistake somewhere in here. The f prime prime is got a mistake in there somewhere. Oh, I lost a 2. No, I didn't. Do that. Oh, I lost an x squared. This is 2x times 2x. This is supposed to be 8x squared. That was my mistake. And so with that, and I didn't, so these guys cancel. We get, I guess we get 2 minus, well, two plus 6x squared over 1 minus x squared to the third power. Yes, this agrees with Wolfram alpha. I think I proved my point, though, in the sense that, do we want to actually calculate these kind of derivatives by hand if we could avoid it? I mean, even for this function, which is relatively simple, you see it's pretty easy to make a mistake even for the second derivative, right? So let me just go ahead and use Wolfram alpha for the third derivative. What do we get? So do you guys know how to do the Wolfram alpha, or do I need to help you? So the syntax I'm putting in is like 1 over, I'm putting in basically this 1 over 1 minus x, x squared. And then I'm doing prime, prime, prime. I'm using prime to calculate the derivative. This will work, Wolfram alpha. So like, I'll walk around here. Okay, so you're okay. Yeah, you can also type out derivative, but this is the prime notation usually works pretty good in Wolfram alpha. If you want a kind of shortcut. Okay.
It's not loading. I ain't tripping. I'll do it later.
Man, this is very annoying. Like the Wolfram alpha sometimes. I don't know why it's not doing that. I feel like I've had trouble with that computer before. Okay, but in any event, when I do the 3 derivatives, I get 24x over 1 minus x cubed. I gotta be careful. It may be x cubed minus 1. Yeah, 1 minus x squared cubed plus 48x cubed over 1 minus x squared to the 4th. Man, my memory. 48x cubed one minus x squared to the 4th. Okay, great. So now that we've got these derivatives, evaluate them at 0. What do we get? Because we were trying to find T3, right? So now, to finish the job, we need to evaluate at 0 and then put the formula together. So like what's, T3 of x, which is equal to what? F of 0 plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared plus 1/6, third derivative, evaluated at 0 times x cubed. What do we get? What's f of 0? 1, right? What's f prime of 0? 0. What's f prime prime of 0? It is minus 2, is it not? Or it's 2. Yeah, it's 2, isn't it? So we plug in 0, we get 2. So we get 1 plus 0 times x plus 1/2. Well, what? Mm-hmm. Yeah, 2 over 1. Very good. Yeah, you're right. It's 2 plus 0 over 1 minus 0 squared cubed, right? But that's 2 over 1, which is 2. And then the third one, well, we plug in 0, we get 0. All right. So what is T3? In this case, it is 1 plus x squared. There you go. Fun fact, this one, in Calc 2, you find out from something called the geometric series that if you want to go on, this is actually equal to 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus dot, 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 like that, provided that the absolute value of x is less than 1. This is from what's called the geometric series. But anyway, that is, of course, forbidden knowledge at the moment. Okay, so anyway, I think I've made my point. We do not want to calculate these by hand, right? So definitely we want to use Wolfram alpha to do the differentiation. Now, you should experiment with Wolfram alpha. You can also do evaluation with Wolfram alpha, right? Like you can say if, try this syntax out. Like if f of x, equals to e to the, well, let's say exponential of 2x, then, f prime of 2, enter. And, well, I'm gonna put the screen up here for a second, but so you guys can just go ahead and try to work out the rest. I don't really have much more to tell you at this point. I'll try to share some suggestions on how to use Wolfram alpha to calculate derivatives, but so here's a syntax for, sorry guys, otherwise the camera can't quite pick up on it. So if I'm using Wolfram alpha and I want to calculate derivatives of a function, here's one way I could do it. Check this out. So I say if f of x equals exponential 2x, then f prime of 2 is what? What is it? Well, it's 2e to the 4th. See that? And then I can check out like f prime prime by just going like that. See? There it is. And I can try the third derivative like this. So, as long as the calculations aren't super lengthy, this is a pretty efficient way of calculating derivatives at a point, right? And if you want to see the symbolic thing, instead of putting a 2 there, just put an x. See? Here it is. Now, I think in your lab, what do we have? Like, part number 3 had what was it? Oh, number 3, you're supposed to actually visualize the, I'm I'm gonna have to put this away here. To do number 4, you'll want to plug in the number 2. Well, or what can we do? So check this out. So like, if I do 1 divided by 1 minus x, 1 minus x squared, like that, and say f prime of 2. So for doing number 4, I think in the lab, see number 4 said, find the Taylor polynomial centered at 3, centered at a equals to 2 for 1 over 1 minus x squared, right? So it's the same derivatives we did, but instead of evaluating at 0, we'll be evaluating at 2. So if we wanted to let Wolfram alpha do the arithmetic for us, we could use this kind of syntax. See this? F of x. Oh man, I got no lasers. Where are my lasers? Oh well. I define the function, I say f prime of 2, it gives me 4/9. You know? Mm-hmm.
You say plot y equals f of x. Which f of x are we using?
The same one as number 2, previous problem. So the 1 over 1 minus x squared. So let's see here. So we had y equals to 1 over 1 minus x squared. I said to make that black, right? Right, so how do we make it black?
No, you said you wanted it red.
I did? Oh, that should say that. I'm sorry, there's a typo right there. I can't do them both in red, right? I meant to make the first one black, and somehow it got lost in. So apparently, thinking to type black and actually typing black are two different things, right? So if you guys could change that red to black, I'd appreciate it. Same for number 5, like plot the function in black. I honestly really don't care as long as you plot all of these things in different colors. Like that's fine by me. But
But like the y of t0 and y of t1.
right. Mm-hmm.
Is that from the stuff that we use like the number 1, the real number 1, or did we already find?
So t0 of x is at the start of the lab. I define those.
Yeah, like that's not. Is
So-
that what it is? Like t0 equals f of a?
Right. T0 is, let's see here, for number 3, f of 0.
It says y equals t0 of x.
Right. But
Equals f of a.
yeah, but let's see here for the one you're thinking. Yes, t0 is f of a. Exactly, it's a constant. For number 2, since the center was at 0, like it's f of a is f of 0. So like it's
So that's the one I'm using.
right. Yeah. Number 2 is number 3 is based on number 2.
Okay.
Yep. So yeah, I think like t0 is y equals to 1, right? And it's kind of silly, but what's t1 equal to? This example is kind of perverse in the sense that t0 is equal to t1. You know?
Is t1 0?
T1's not 0. T1 is equal to 1 again. Because T1 is f of 0 plus f prime of 0 times x. So it's T0, I mean T1 of x is equal to 1 again. It's a quirk of this function that T0 and T1 are the same thing. If I could follow my own color coding. red, blue. Hmm. So if you graph T1 after T0, it's going to like overwrite it, you know? It does. Either way is fine. It's just that the graph of T0 and T1 are the same, you know? T2, though, that's more exciting. What's T2? So T2 here is 1 plus x squared. And so, you know, for this one, when you graph T3, it doesn't really change anything because T3 is equal to T2 here as it happens. So once you've graphed T0 and T2 and the function, you've produced all the curves that you're going to see. This one's not especially exciting, but I would point out, you can kind of see how, you know, this green line, so the constant approximates the function close to the point, right? But the green one, it stays with it a little bit further out, right? So I think when you get to number 5, it's a little bit more exciting because in number 5, the T0, the T1, the T2, and then I said T4, I meant T3 there. Good grief. That's supposed to be T3 in number 5, yes. Yeah, that's supposed to be T3. I am sorry. I don't know how that got there. Because I wanted it just to, my intention here was just for you to graph what you'd already calculated in part 2.
So for T3, we're just plugging in 3, so 1 plus x squared?
You're plugging in 0, well, you're just putting in, y equals 1 plus x squared. Because the third derivative is 0, so it happens that T2 of x is equal to T3 of x for number 3. Yeah. Yeah. So the thing is, as we're building the kth order Taylor polynomial, you can always see the zeroth, the first, the second, the third, the fourth, as you just go across the terms. Like all of the lower order Taylor polynomials are the start of the kth one. You know, so we get to see all of the Taylor polynomials as we're building the formula. All right, well, I'm going to put this away. Actually, I'm gonna hit I think that should cover it. You know, I'm going to let you guys work on it, basically, but I'm not going to record any more past here, so.